Hey y'all, welcome back. So today we're going to start a new unit all about rational functions. In our last unit, we briefly looked at rational functions, but within the context of trying to solve an inequality. We didn't really take a look at what the graphs of these functions look like, and that's what we're going to focus on in this unit. So today, we aren't going to actually put pen to paper and sketch out any of these graphs yet, but what we are going to do is learn how to identify all of the important characteristics of the function so that we can graph them in the next lesson. So just to sort of define what a rational function is, a rational function is basically like a big fraction where both the numerator and the denominator are both polynomials. So they can't be like square root functions or absolute value functions. They have to be polynomials in order to be considered a rational function. The other little, just a little detail here is that this denominator can't be 0, okay, because then the whole thing would be undefined. So when we're talking about the domain of rational functions, it's going to be all of the values on the real number line typically, except for the values that make the denominator equal 0, because that's going to make the whole function undefined. So let's go through all of the important characteristics of rational functions. Okay, these are going to be all the details that you're going to have to include on your graph when we start graphing these functions in the next lesson. So the first things that we're going to try to find are the intercepts of the function, the x-intercepts and the y-intercept. Now we can have multiple x-intercepts, and we learned in the last unit actually how to find these, so this is going to be a little bit of a review. But we didn't really get into the y-intercept, although you find it the same way that you find any other y-intercept. So to find the x-intercepts, those are going to be the points that lie along the x-axis, and the points that lie along the x-axis all share the same y value, which is 0. So one way to think about this is you're going to set the y equal to 0 and solve for x. But in every case, when you have these fractions and you set the whole thing equal to 0, the first step's always going to be to multiply both sides by whatever the denominator is, and 0 times whatever the denominator is 0. So there's a little bit of a shortcut we can take here. And so to find the x-intercepts, what you're going to do is you're going to set the numerator equal to 0 and then solve for x. Okay, so this is, like I said, this is something we already did, so hopefully this is not anything new. To find the y-intercept, instead of setting the y equal to 0 and solving for x, we're going to set x equal to 0 and solve for y. Now, these rational functions should already have y isolated, so there shouldn't really be any solving going on. You just really need to evaluate. So to find the y-intercept, you're going to set x equal to 0 and evaluate the function. So basically, you're going to plug in 0 into x and just compute what you have. You're going to find the y value of the coordinate when x is 0. So this one's pretty straightforward too. In fact, most of these characteristics will be pretty straightforward how we find them. There's only a couple of them that will take a little bit more effort. Now the vertical asymptotes are going to be lines. One moment. The vertical asymptotes are going to be lines that cause the function to either go to positive infinity or negative infinity. So the way to find these vertical asymptotes is you're going to set the denominator equal to 0. Set the denominator equal to 0 and then solve for x. This is what we did in the last unit. Now, we didn't differentiate between vertical asymptotes and what we're about to talk about, which is holes. And so we'll do that now. But these values that we're finding when we set the denominator equal to 0 and solve are going to be all the values that make the entire function undefined. So going back to what I was talking about, the domain will be all x values, like from negative infinity to infinity, except for the values that you get here. So we would exclude those from the domain. Like I said, we'll get into the graph next time, but right now we're just going to focus on how do we find each of these characteristics. So one thing that came up in the last unit when we were solving rational inequalities is that occasionally you'll have an x value that makes the numerator equal 0 and the denominator equal 0. And the only thing I really said in the last unit was that in that case, that the function is going to be undefined, because what we end up with when we plug in that particular x value is a situation where the numerator is 0 and the denominator is 0. And since 0 divided by 0 is undefined, we sort of just said, okay, well, it's going to be undefined. It's not going to be an x-intercept, but that was as far as the discussion went. But today we'll get a little bit more in detail. I'm like, okay, well, what is actually going on there? So, and I guess I'll just type this out. If an x value makes both the numerator, the numerator and the denominator equals 0. So if an x value makes both the numerator and the denominator equal 0, there is a hole in the graph at that x value. And so when you have a hole there, there's not going to be an x-intercept, and there's actually not going to be a vertical asymptote either. So this hole is going to sort of override both of those. So there's a hole at the graph of the x value instead of an x-intercept or a vertical asymptote. Now, the function's still going to be undefined there because a hole doesn't have any value. So what's kind of challenging about the hole is trying to find the y value of the hole so that we can plot it on our graph. Now, like I said, we're not actually going to be plotting graphs today. We're just going to be focusing on finding the characteristics, and we'll get to the graphs next time. But to find the y value of the hole, what you need to do is first factor the rational function and then cancel out each of the factors that are the same. So let me just kind of spell that out here. So to find the y-coordinate of the hole, first factor the rational function. Now, when you factor it, what you're going to notice when you have a hole is that you have a factor, like let's say x minus 3 or something like that, that's going to appear in both the numerator and the denominator. And so that's why we're getting 0 in both cases. So, this will probably make more sense once we actually get to an example where this happens. But what you do is you take that rational function and you sort of temporarily cancel out or reduce to 1 those two factors. And then whatever you're left with is going to be this new equation that is equivalent to the original equation, except it has the hole filled in. So what I'll call that equation is the hole equation. Again, when we start getting into the examples, I think you'll understand this a little bit more clearly, but I just wanted to spell out exactly what you do to find these. So first you factor out the rational function, then temporarily cancel out the common factor to create what I'm going to call a hole equation. And what this hole equation is it's exactly the same as the original equation or function, except the hole is filled in, so that when you plug in the x value, you're not going to get an undefined result. You're actually going to get a y value, and that y value will be the y-coordinate of the hole. To cancel out, so let me make sure, reread this. To find the y-coordinate of the hole, first factor the rational function, then temporarily cancel out the common factor to create a hole equation. Then you're going to plug in the x value, where the hole is, into the hole equation. And evaluate to find the y-coordinate. So there's one more characteristic that we'll need to find, and that's the horizontal asymptote. This one will take the most amount of effort to sort of remember how to find it. But basically, with these rational functions, typically you'll have one or more vertical asymptotes, but you'll only have one horizontal asymptote, if there's one at all. So to find out whether or not to find what the horizontal asymptote is, what you're going to do is you're going to look at the degrees of the function. So make a note of the degree. Come on, there we go. Of the numerator and the denominator. Now, what I mean by degree is the largest exponent. So like if you have like x to the fifth, and that's the largest exponent in the polynomial, then 5 would be your degree. So depending on how the two degrees compare to each other, like the degree of the numerator and the degree of the denominator, you will decide what the horizontal asymptote is. So when you're comparing two numbers, there are three different options that could potentially happen. Either the numerator is going to have a larger degree, or the denominator will have a larger degree, or they'll be the same. So let's start with sort of the simplest case, and that is when the denominator has the larger degree. So if the denominator has the larger degree, then the horizontal asymptote will be y equals 0. Okay, in other words, it will just be the x-axis. So it'll just be like flat. Obviously, it's going to be horizontal. We're talking about horizontal asymptotes, but it'll just be y equals 0. Now, the reason for that is because if the denominator has the larger degree, then its rate of increase is going to be larger than the numerator. And so what I mean by that is as x gets larger and larger and larger, the denominator's size is going to get way bigger than the numerator. In fact, the distance, or the difference rather, between the value of the denominator and the value of the numerator will increase. And so as the numerator gets tremendously bigger than the numerator, then the entire value of that is going to approach 0. So that's why the horizontal asymptote will be y equals 0. Now, if the denominator has the same degree as the denominator has the same degree as the numerator, then the horizontal asymptote will be found by finding the ratios of the leading coefficients. So let me just write that down. I'll do a little explanation here. So the horizontal asymptote will be y equals, and then we'll have a fraction here. In fact, I'll probably have to type this in as a little equation here. So y equals the leading, well, this is not going to be very easy to do that. I guess I'll go back to the text. Will be y equals, and then we'll have a fraction like this. Oh, that's a little too long there. Let's try to make this look nice. And then it's just going to be a fraction, like your answers are going to be like 2/3, or it could be a whole number like 2, but basically where you're going to get the numerator and the denominator from are the leading coefficients of the numerator and denominator. So the leading coefficient of the numerator divided by the leading coefficient of the denominator. So basically, like if you've got two polynomials and you've got something like 3x squared over 5x squared, the x squareds are going to increase at the same rate. So when you're thinking about like how the difference between the two, the numerator and the denominator will be changing, the difference between them is not going to be changing much at all, and you're going to approach whatever the value of that ratio is. So like in that case, your asymptote will be at y equals 3/5. And as we've looked through a couple examples, you'll see kind of how that gets computed a little bit more clearly. Now, lastly, there's one other way that they can compare, if the denominator has the smaller degree. So this would be a case where you have something like, x to the fifth over x squared, or something like that. In that case, the numerator is going to grow at a faster rate than the denominator. And what happens here is kind of weird. For now, we're just going to say that there is no horizontal asymptote. Now, there is an asymptote that exists. It's just not going to be horizontal. It'll be some other shape, like it might be a line, like a diagonal line or a slanted line. It might be parabolic. It might be cubic. It kind of depends on what the degrees of the numerator and denominator are, and you can find what the equation for that other asymptote is. But for right now, we're just going to say that there's just no horizontal asymptote. There is an asymptote there. It's just not horizontal. It might be linear. I guess horizontal would technically be linear, but like a diagonal line, or like I said, it could be parabolic or some other shape. But for now, we're just going to say that there is no horizontal asymptote, and leave it at that. All right, so that's it. So depending on what's going on with the degrees of the numerator and the denominator, we can decide what the horizontal asymptote is going to be. And so we'll have to make that decision as we find horizontal asymptotes of these functions. So let's, before we get into the examples, one last thing here is the horizontal asymptote is going to determine the end behavior of the rational function. So when we were talking about polynomials in the last unit, generally, in every case, as x approached infinity or negative infinity, the value of the function either approached positive or negative infinity. But for a rational function, it still could approach positive or negative infinity when your asymptote's not horizontal. But I'll say if, still in the equation mode here, if there is a horizontal asymptote then as x approaches infinity, and this could be positive or negative infinity, so it's going to typically do the same thing to the left and to the right. In fact, for rational functions, I think that'll actually always be the case. So as x approaches positive or negative infinity, the value of the function, or f of x, will approach the horizontal asymptote. So the horizontal asymptote. So if your horizontal asymptote is 2, then the value of the function will approach 2. Did I spell? I don't think I spelled that right. There we go. All right, so that's it. That is all of the characteristics that you'll have to find. The first few are going to be pretty straightforward. When you find the x-intercepts, the y-intercept, the vertical asymptotes. The whole will take a little bit of extra work, and you'll have to think a little bit about these cases to find the horizontal asymptote. So let's jump into some examples here. So we're going to analyze this rational function by coming up with the intercepts, the asymptotes, the holes, if there are any. And it is possible that there aren't any holes. It's possible there's not a y-intercept. It is possible that, I guess x-intercepts, yeah, you may not have an x-intercept. You always have a vertical asymptote. Yeah, I guess most of the time you will. I guess there are some cases where you wouldn't, but I think all of these are going to have one. So basically, don't think that you will have a value for all of these. It is possible that some of them don't. Now, to get started with this analysis, the first thing you always want to do is factor the polynomial. It'll just make finding all these things a lot easier. So let's factor this first one. The numerator is 2x, so that's not really going to change because that's already factored. But x squared minus 16 is a difference of 2 squares. So we can factor that as x plus 4 times x minus 4. And this will just kind of help everything go along. So to find the x-intercepts, we're going to set the numerator equal to 0 and solve. So we're just going to get x equals 0. Okay. So my x-intercept is going to be at 0, 0. To find the vertical asymptote, there we go. To find the vertical asymptote, we're going to set the denominator equal to 0. So I'm going to set x plus 4 times x minus 4 equal to 0, and I'm going to get x equals plus or minus 4. So x equals 4, x equals negative 4. Now, these are going to be lines rather than coordinates. So we want to make sure when we express what the vertical asymptote is that we write it as a line. And so the way that you write a line is as an equation. So we're going to say there's a vertical asymptote at x equals negative 4, and there's going to be another vertical line at x equals negative 4. So these are going to be the two vertical asymptotes. So asymptotes you'll write as equations, intercepts and holes you'll write as coordinates. Now notice that there was no value, no x value, that will make both the numerator and the denominator equal 0. In other words, like we don't have a duplicate value on these two lists. So when that happens, you can say right away that there's just no hole, okay? Holes will only exist if there is an x value that makes both the numerator and the denominator 0. To find the y-intercept, we're just going to substitute in 0 into x and then evaluate it. So we have like 2 times 0 divided by 0 squared minus 16. And, you know, if you've got an x-intercept that is 0, then you know right away what your y-intercept is going to be. It's going to be 0. But I just want to kind of go through and show you like how you would compute it if it wasn't going to be that. So this is just going to be 0 over negative 16, which equals 0. So we get the same exact point that we got for the x-intercept, which should be what you were expecting anyway, because basically what's happening is this graph is going to cross at the origin. Okay, so the horizontal asymptote. So for the horizontal asymptote, we need to look at the degrees of the polynomial. So the degree of the first, the degree of the numerator is 1, because we just have 2x, like to the first power, and the degree of the denominator is 2. So because the degree of the denominator is bigger, then this thing is just going to approach 0. So the horizontal asymptote is going to be y equals 0. All right, and that's it. So we've found all the important characteristics here. That's all we really needed. Let me zoom out so you can actually see that vertical asymptote. I didn't realize that was getting cut off there. Let's see, can we get somewhere in the middle there? Nope. All right, well, I'll just pull it out like this, I guess. That's kind of weird. Or you know what might be a better option here is just to drag it over. So we can, there we go. Okay, so all we're going to do with all of these is the same sort of process. We're just going to find our intercepts, we're going to find our asymptotes, holes if there are any, and then that's it. We're not going to actually graph this until next time. So let's take a look at a few more examples here. Now, when we start these problems and when we start to do the analysis, just like with the last one, we want to make sure to factor both the numerator and the denominator up front. And like I said, it'll just make everything go a lot more smoothly. So the numerator here can be factored as x plus 2 times x minus 1. And the denominator will be x, let's see here, I guess that'll be minus 3 times x plus 2. So what I'll point out here is that you may notice that we've got a factor on the numerator and the denominator. So that's going to come into play when we get to the holes, but not quite yet. So we'll find our x-intercepts first by setting the numerator equal to 0, and then solving that equation. So we're going to end up with x equals negative 2 and x equals 1. So my two x-intercepts are going to be at -2, 0, and let's see here, and 1, 0. All right, so there we go. There's my x-intercepts. My vertical asymptote is going to be where the denominator equals 0. So I'm going to set that denominator equal to 0. And solve for these values. I get x equals -2 and x equals 3. Now, you might notice, again, at this point, that we have a little bit of a contradiction here because we can't have an x-intercept at the same location that we have a vertical asymptote. So these vertical lines, -2 and 3, only one of these is actually going to be a vertical asymptote. Notice here that we've got this -2 in both lists, right? So we've got -2 here, and we've got -2 here. So that means that at -2, we are actually not going to have an x-intercept or a vertical asymptote, and instead we will have a hole. So these are just like, we're going to cross these out of our list. So let's go down before we get to the y-intercept and the horizontal asymptote and say, okay, well, we know we have a hole at x equals -2. Okay, but the question is going to be, where's the y-coordinate, right? If I try to plug in -2 into this equation, it's going to be, it's going to give me undefined, right? Because I can't divide by 0. So to find the whole equation that I can use to actually plug that in, what I'm going to do is take the factored, there we go. Take the factored expression and just sort of temporarily cancel out these, and I'll be just left with x, so y equals x minus 1 over x minus 3. And this is going to be an equation that I can use to find the y-coordinate of the hole. So since I know the x value of the hole is at -2, to find the y-coordinate, I'm just going to plug in -2 here. So I'm going to get -2 minus 1 over -2 minus 3. And so this is going to be y equals, what would that be? -3 over -5. So negative divided by negative is positive, so we get positive 3/5 here. So there's a hole at -2, -2 comma 3/5. All right, so let's make sure, try to fix that color. All right, so that's how you find the y-coordinate of the hole. We're only going to have one x-intercept and one vertical asymptote here. So again, just to really emphasize this, when you get the same factor in the numerator and the denominator, that's going to cause a hole rather than either one of these two things. So to find the y-intercept, we're going to plug in 0 into our equation. Now, to find the y-intercept, it's usually going to be easier to plug in 0 to the original equation versus the factored one. And the reason for that is because since all the x's are zeros, you really only have to look at the constant terms in both the numerator and the denominator here. So if y is going to equal, 0 squared plus 0 minus 2 over 0 squared minus 0 minus 6, notice here that really we just need to look at, these terms right here, right? Because this is all 0. So we're going to say that the y-intercept is going to be at 2 over 6, which reduces to 1/3. And so my y-intercept is going to be at 0, comma 1/3. The horizontal asymptote is going to depend on the degrees of the numerator and the denominator. So what I might do here is just copy this. I don't have to retype the whole thing again. And in this case, the degrees of the numerator and the denominator are the same. Okay, so what we need to do is we need to look at the leading coefficients of the numerator and the denominator. So since the leading coefficient of the numerator is 1 and the denominator is 1, the horizontal asymptote is going to be at y equals 1 over 1, which is just y equals 1. So it's going to be a horizontal line right above the x-axis. Okay, so that kind of wraps up this problem. Let's go on to another example. Okay, so here we are going to factor first, just like the last one. Two numbers that multiply to give me negative 56, but add up to 1 are going to be 8 and negative 7. So x plus 8 times x minus 7. To factor the denominator, we are going to need to first find factor out the GCF of x. And so if I factor out an x, I get x squared minus 8x plus 7. And so I need to, now I can factor this a little easier. That x is still going to kind of hang out there. So I'll just say it equals, let's see, this whole thing. There we go. Except I'm going to factor this denominator here. So I've got two numbers that multiply to give me 7, but add up to negative 8. That's going to be negative 7 and negative 1. So x minus 7 times x minus 1 are going to be my factors. You'll notice here that we have an x minus 7. So that's going to be, there's going to be a hole there. And so really to find the x-intercept, I just want to set x plus 8 equal to 0. On the last problem, I went ahead and just like solved the whole thing, but I want you to kind of be on the lookout for these holes so that you don't have to do any extra work. Like up here, you know, if I had noticed that I had x plus 2 over x plus 2, I could have just skipped setting x plus 2 equal to 0 because I know there's going to be a hole there anyway. So I've got an x-intercept at x equals negative 8. And so I'll just write that as a coordinate, negative 8 comma 0. I'll have a vertical asymptote where the denominator is 0. Again, I'm going to skip over this x minus 7 factor because I know that there's actually going to be a hole there rather than a vertical asymptote. So I'm going to get two vertical asymptotes here. I'm going to get one at x equals 0 and one at x equals negative 7, positive 7. Oh, wait, no. I got the wrong one here. This should be my x minus 1. So there'll be one at x equals 0 and x equals 1. So my two vertical asymptotes are going to be at x equals 0. So a vertical line there. Now, the fact that I have a vertical asymptote at x equals 0 tells me that I'm not going to have a vertical asymptote. I'm sorry, not a vertical asymptote. The fact that I have a vertical asymptote there means I'm not going to have a y-intercept because I cannot cross a vertical asymptote. Now, you might be wondering, hey, wait a minute. We had on a previous problem, we had a horizontal asymptote along the x-axis, but we had an x-intercept. What's going on there? Well, the fact is you can actually cross a horizontal asymptote, and this particular one does. But what you cannot cross is a vertical asymptote. And that's really due to the definitions of these asymptotes and like what a function is. You cannot, like if I were to have a vertical asymptote and cross over it, I'd have to like come back and right away I would break the vertical line test and it wouldn't be a function. So anyway, we cannot cross vertical asymptotes, but we may cross horizontal ones. So I get two vertical asymptotes here. I already know there's not going to be a y-intercept, but just to kind of show you that, that is what happens. If I plug in 0 everywhere, what I'm going to do is I'm going to end up with a 0 in the denominator. And since we can't divide by 0, we're just going to say, no, never mind. There's no y-intercept here. So let's see, plus 7 times 0. So this is going to be negative 56 over 0. Can't divide by 0, so we're going to say there's no y-intercept. For the horizontal asymptote, we're going to take a quick look at the degrees. And so once again, we're going to look at, just so I don't have to retype all this, the degree of the numerator here is 2, and the degree of the denominator is 3. So since the degree of the denominator is bigger, then the horizontal asymptote is going to happen at y equals 0. All right. Now, lastly, we're going to find where the location of the hole is. Now, we know that the x value here is going to be 7, right? Because that's the value that would make both of these 0. So we know that there is a hole at x equals 7. Let me just double check, make sure that, yep, that's 7. So let's find our little hole equation. Okay, and we get that by just simply canceling out the common factor here. Now, this equation that I'm typing is not going to be the same in the sense that it's always equivalent, because it won't be. This one will have the hole filled in. It'll be almost the same. It'll be almost exactly the same as the original function, but it won't have that hole, which means we can go ahead and plug in 7. So to get the y value here, or the y, I guess I'll say the y coordinate, we're going to plug in 7 into this equation here. So y is going to be 7 plus 8 over 7 times 7 minus 1. So that's going to be 15 over 7 times 6, right? So 15 over 42. Does that reduce? 6 times 7. I guess they're both divisible by 3. So that'd be 14. Is that right? 14 times 3. 3 carry 1. Yeah, I think that's right. Okay, so that's the y coordinate of the hole. So my hole is going to be at 7, so it's the x value, comma 5 over 14. All right, so there's not really, much new to talk about here. I just have 2 more examples for you, so we can kind of just see how a few more of these work out. Let's see. So this one we're going to factor, and we're going to get x plus 2 times x plus 1. So we are going to have a hole in this one as well. Now, they won't all have holes. We've already seen one that didn't. So don't expect that you're going to get a hole in every single one. This one's kind of interesting because when this one's just going to basically be a line. There's not going to be any asymptotes here. And it will just have a hole at -1. But we can still find most of the other characteristics here. The x-intercept will be the place where x plus 2 equals 0. I'm going to ignore the x plus 1 because I know there's going to be a hole there. So I've got x equals, let me keep moving here, x equals -2, which means I've got an x-intercept at -2 comma 0. The vertical asymptote will be where the denominator is 0. So, if I would have x plus 1 equals 0, but I know that there's going to be a hole there anyway, there's no other factors for me to work with, so there's just no vertical asymptote. The y-intercept will be the value of the function when I plug in 0 into the equation. So the y-intercept is going to be 0 squared plus 3 times 0 plus 2. Again, you can really just look at the constants here, the 2 over 1, because everything else is going to be 0. So yeah, all this is going to be, this is just going to be 2 over 1, which is just 2. So my y-intercept is going to be at 0 comma 2. A horizontal asymptote, we're going to look at the degrees, and the degree of the numerator here is going to be bigger than the degree of the denominator. So that means there's not going to be any horizontal asymptote either. So no vertical, no horizontal asymptote. We'll look at the graph next time, or not the graph of this particular one, but one that's like this next time. So you can kind of see what's going on here. But basically, it's going to be the graph is going to look exactly like a line, and it'll have a hole in it. So we've got degree of the numerator is 2, the degree of the denominator is 1. So when the degree of the numerator is bigger on top, we're going to say that there is no horizontal asymptote. I don't know why I made all that caps there. Let's see. No. Okay. The last thing to find here is the hole, and we can see that we're going to have a hole at x equals -1 here. So just to save myself a little bit of time, just copy all this. So the hole is going to be not at x equals 7, but at x equals -1. My hole equation will be what I get when I cancel out the x plus 1s, and so all I'll have left is just x plus 2. And so that's how I know this graph is just going to look like a function. Like a linear function, like a line, because the whole equation will look exactly the same except for the holes filled in. So because the whole equation is x plus 2, I know that's a linear equation, like mx plus b. And so I know what the graph is going to basically look like here, except we're going to have a hole at -1. So I'm going to plug in -1 into x here, and I'll get y equals 1. And so my hole location is going to be at -1, 1. All right, one last example here. Let's see what we've got here. All right, for this one, we're going to start by factoring out an x squared from the numerator. So we get x squared minus 5x plus 6. And the denominator will go ahead and, oh wait, look at that, Wait, it looks like, are we going to have 2 holes? I think so. So we get x plus, the way this is going to factor is going to be x minus 6. Oh wait, no, what would it be? X minus 3 times x minus 2, yeah. -3 times -2 is 6, and they add up to -5. So that's actually the same trinomial that we have above, kind of a weird problem here. So we actually are going to end up with 2 holes, right, and no vertical asymptotes. All right, so my x-intercepts, I'm going to ignore the duplicate or the repeated factors here. So I'm going to ignore x minus 3 and x minus 2. And so the only x-intercepts I'm going to get are where x squared equals 0, which means x is 0. So I get an x-intercept of 0, which right away is going to tell me what the y-intercept is because I already have it, right? Like this is where it's crossing the y-axis as well. But you can always double check if you don't believe me and say, okay, well, 0 to the 4th minus 5 times 0 cubed. So really we have so far 0 plus 0 plus 6 times 0. So the numerator is going to be 0. And the denominator is going to be positive 6 because we've got 0 squared minus 5 times 0 plus 6. The only constant there that's not 0 is the 6. So this is going to equal 0 over 6, which, like I said, is just going to be 0. So the x-intercept and the y-intercept are the same point. You don't have to go through all this if you notice that. If you got an x-intercept that's at 0, right away you can just say, okay, well, that's going to be the y-intercept as well. For the vertical asymptotes, normally we would set the denominator equal to 0, but since we know there's going to be holes at 3 and at 2, and there's no other factors left, we'll just say there's no vertical asymptote. And for the horizontal asymptote, let's see, the degree on top is bigger, right? The degree of the numerator is going to be 4, and the degree of the denominator is going to be 2. So let's see, degree of the numerator is 4, degree of the denominator is 2, so it's bigger on top, so there's going to be no horizontal asymptote on this. So 2 problems back to back with no asymptotes. That's kind of not very fun, but that's all right. So we do end up with 2 holes here. We're going to end up with a hole at x equals 3 and one at x equals 2. So the whole equation here is going to be what we get when we cancel out the x minus 3's and x minus 2, so we just end up with x squared. So this graph is actually going to look like a parabola, but with these 2 holes kind of in the mix here. So we've got a hole at, not -1 here, but what was it? At 3 and at 2. So there's 2 of them here. The whole equation is going to be what we get when we cancel out the x minus 3, x minus 2. So we're just going to get y equals x squared. Which means that all we really need to do is square the x values here to get the y coordinate. So we actually have 2 of them here, so just to clean up the grammar here, the y coordinates, or I guess y coordinate of the holes. There's 2 of them. I'm not really sure on the grammar there, but I'll just leave it alone. So the first one, we're going to say y equals 3 squared, which is 9. And so, for the second one, we've got y equals 2 squared, which is 4. So we've got 2 holes here. We've got a hole at 3, 9, and another hole at 2, 4. So you may get multiple holes. And it really just depends on how many of these factors are common to both the numerator and the denominator. So that's pretty much it for today. Hope you all are getting a better idea of how to find all of these different characteristics. Next time, we are going to do kind of the same thing that we're doing today, except we're going to put all these on graphs. So yeah, I guess that's it. If you guys have any questions, as always, let me know. But otherwise, have a great day, and I'll see you next time.